In this video, we're going to talk about substitution rule for integration formally, as well as do example 1 and example 2, which is a slight variation on example 1. So our substitution rule for integration corresponds to our chain rule for differentiation. We're undoing chain rule. Remember that chain rule is used when you're taking the derivative of a composition of two functions. For example, if I have the derivative of f of g of x, that's a composition of two functions, I'm going to take the derivative of the outside function evaluated at the inside function, chain rule, times the derivative of the inside function. In particular, if big F is an antiderivative for little f, then we have this. Right? If the derivative of the antiderivative will be our original function. Okay, so how does substitution rule work? If u is some function of x that is differentiable and its range is an interval where the function f is continuous, then we can make the following substitution. Don't stress about that. You're going to be able to make the following substitution. If I'm integrating f of g of x times g prime of x dx, I can make the substitution where u is g of x, du is g prime of x dx, much in the same way that we did in our previous example when we were exploring how to do chain rule backwards. Here is your goal. Let me try to simplify things for you. You're looking for a choice of u such that we have du, the derivative of u, as a factor. This is important, that this is multiplication. A factor in the integrand. Let's write that. Here's your goal. Choose your u is equal to some x stuff in such a way that the derivative of u with respect to x, whatever that is being multiplied in the integrand, is a factor in the integrand. Remember, integrand is just a fancy word for the function that you're integrating in the integrand. That's your goal, right? Just made it a little bit smaller. And just like any sort of substitution, you always do substitutions to make your life a little bit easier, especially visually. Substitutions only work if you substitute completely, right? So make sure you substitute completely. Integrating some x and some u stuff is nonsense. All right, you got to make it. If I'm going to make a substitution, u has to be in everywhere in that integrand. All right, so let's go ahead and do an example. Integrate cosine of x squared times 2x. So what this is asking me for is the family of functions whose derivative is cosine x squared times 2x. I'm going to do a u substitution here, a little scratch. I want to choose a u such that when I take its derivative, I see times du. So notice that if I let u be x squared, then the derivative of u with respect to x is 2x. So the derivative, so du is a 2x dx. And notice that I have that 2x dx sitting right here. Scratch. All right, so making the substitution, I'm going to integrate cosine of u and then times du. Delightful. The derivative of what function is cosine u? The derivative of sine u is cosine u. Moreover, the derivative of sine u plus any constant would be cosine u. But u, this substitution was just a tool. We need to go ahead and back substitute. What the heck is u? U is x squared. And we are done. You can always check by differentiating. Let me make this a little smaller. If I take the derivative of sine x squared plus a constant, do I get, and I'll leave the check here to you, do I get cosine x squared times 2x? All right, so now let's do a slight variation. Let's integrate cosine x squared times 6x. Well, this is a little more frustrating because if u is x squared, du will be 2x dx, and I have a 6. But that is entirely okay because 6x is a constant multiple of 2x. So let's go ahead and try this again. All right, so a little scratch. I'm going to go ahead and let u be x squared. The derivative of u with respect to x is 2x. So the derivative of u, or du, sorry, is 2x dx. I am doing a little hand waving there. And I don't exactly have 2x dx there, but I have 6x dx. If I go ahead and multiply both sides by 3, I've got 3 du is equal to 6x dx. And that is exactly what I have right here. Okay? If you're watching other videos or reading other texts, sometimes people like to make their choice of u and du and go ahead and substitute in and hope that all the x's cancel and simplify. That's a perfectly fine technique. The reason why I'm doing it this way is I'm really trying to emphasize chain rule, where we have times the derivative of the inside, or times a constant multiple times the derivative of the inside, because integrating a constant times a function is just the constant times the integral of the function. But it really is a matter of style, and this is really only our second one that we're seeing here, so please don't decide this is too complicated. You can do it. I know you can. Alright, so here we have it. The integral of cosine of green, that's cosine of u, times a 3 du. This is all multiplication, order doesn't matter, and in fact you can pull that constant multiple out in front, but maybe I'll just write it like this: 3 cosine u du, which is 3 times the integral of cosine u, du, and this is the whole purpose of doing it. The derivative of what function is cosine? Oh, the derivative of sine is cosine. So we've got our constant multiple times sine of u plus a c. The derivative of 3 sine u plus any constant would be 3 cosine u, right? Plus 0, which is 3 cosine u. But u is just a tool. You're going to want to go ahead and back substitute. We've got 3 times the sine of u, where u is x squared, then plus any constant of integration, and we are done. Now I'll leave the check to you. What do you want to check? If you differentiate this antiderivative, this general antiderivative, you should end up with cosine x squared times 6x.